This is video 4 of our probability series. We'll start on page 8 of our guided notes. We're going to talk about conditional probability and the multiplication rules. We'll look at 2 examples. First, we're going to talk about the examples, then we'll revisit them and actually calculate answers. First, example 10, you're going to roll 2 die. What's the probability that you will get a 5 on each die? The probability of a 5 on the first die and a 5 on the second die. The outcome of a 5 on the first die does not affect the probability of getting a 5 on the second die. These events are independent. They're 2 separate dice. 2 events are called independent if the occurrence or non-occurrence of one doesn't change the probability that the other occurs. Our second example we're looking at, example 11 here. You draw 2 cards from a standard deck without replacing the first card before drawing the second card. What's the probability that both of these cards will be aces? So here we're looking at the probability of an ace on your first card and an ace on the second card. The probability of an ace on the first card, well, there's 4 aces out of 52 cards in the deck. So the probability is 4 out of 52. And the probability of an ace on a second card, given that you got an ace on the first card, well, if you've already drawn that first ace, then there's only 3 left in the deck. And if you've already taken out 1 card, there's only 51 cards left in the deck. So the probability of getting an ace on that second draw will be 3 out of 51. In this case, the events are not independent, but rather they are dependent. The outcome of the first draw changes the probability of getting an ace on the second draw. Notice in both of these examples, I highlighted "and" in the written probability. These 2 examples are alike in the fact that you're finding the probability that 2 events occurring together. That's why we have that "and" there. Example 1 has independent events, and example 2 has dependent events. So as you'll see, we'll have slightly different processes. The independence or dependence of events matters in how we're going to compute the probabilities of these 2 events or more happening together. So for independent events, we have the probability of A and B is equal to the probability of A times the probability of B. So when we see that "and" word in our probability statement, we're going to multiply. And for independent events, the probability of A is equal to the probability of A given B. Why? Because it doesn't matter if B happened or not. So the probability of A doesn't change based on B. In general, we won't always have independent events, so we have a general multiplication rule. The probability of A and B is equal to the probability of A times the probability of B given that A happened. The probability of A and B is equal to the probability of B given that B times the probability of A given that B happened. So really, when you're finding probabilities for these multiplication type problems, you're always considering how one event impacts the other. So if events are dependent, then we have to take into account the changes in the probabilities of one event caused by the occurrence of another. So the notation, probability of A, we use a vertical line, given B, denotes the probability that an event A will occur, given that B already occurred. We call this conditional probability, and this video is all about conditional probability. Here are some manipulations of that conditional probability formula I just gave you, but let's take a look back at those examples. Our example labeled example 10, you roll 2 die, what's the probability of getting a 5 on each die? Well, we have the probability of a 5 on the first and another 5. Probability of a 5 on the first would be 1/6 because there's 1 5 out of the 6 sides. And tells us to multiply. And then we'll have a probability of 1/6 on the other die. So 1/6 times 1/6, let's see, we just multiply across the numerator, multiply across the denominator, and then simplify as needed. We'll get the probability of rolling a 5 and a 5 will be 1 out of 36. For example 11, we draw 2 cards from a standard deck without replacing the first card before drawing the second. What's the probability that both will be aces? So a probability of an ace and an ace. And I'm going to write without W/O replacement as a note to myself. The probability of the first card being an ace would be 4 out of 52, because there's 4 aces in the deck out of 52 cards. And tells me to multiply. Because it's without replacement, if I take out an ace, I'll only have 3 left. And then, since I already took out a card, I'll only have 51 cards left. So the second ace has a probability of 3 out of 51. Now multiply. We go across the numerator, across the denominator, and then we simplify. Our simplified answer is 1 divided by 221, or approximately 0.005. A hot tip for using your calculator. If you need a fraction answer and a simplified fraction, you can go ahead and type the calculation in, and you can see here we got our decimal answer. Now go over and press Math, and then you'll see the first option says Frac. Press Enter on it, and then press Enter one more time, and that gives you the simplified fractional answer. 1/221 in this case. Some more rules to follow. For multiplication, rules apply whenever we want to determine a probability of 2 events happening together. Use "and" between events to indicate together. Before using multiplication rule to compute the probability of A and B, determine if A and B are dependent or independent. Round to 3 decimal places for probabilities as a general rule unless otherwise stated. The 5% guideline for cumbersome calculations. This is important. When sampling without replacement and the sample size is no more than 5% of the size of the population, treat the selections as being independent, even though they're actually dependent. And example 12 here has to do with this. In a particular city, 78% of the adult residents are registered to vote. What's the probability that you randomly select 4 adults and all are registered to vote? Now, if we select 4 adults out of our whole city's population, that's going to be less than 5% of the population. So we can treat these selections as being independent of each other. So that means for the first adult, second, third, and fourth, they're all going to have the same probability of being registered. And the probability of one being registered to vote is 0.78. So what we'll end up with here is 0.78 times 0.78 times 0.78 times 0.78. An easier way to write that out would be 0.78 to the 4th is the probability of all 4 being registered. That rounds to 0.370. In our calculator, we can type 0.78, and then this caret button is an exponent, and then 4, enter. And that gives us our answer. For part B, it says, what's the probability you randomly select 2 adults and neither is registered to vote? So if you're registered to vote, the probability is 0.78. So the probability of not registered will be 1 minus 0.78, which is 0.22. So the probability that there's 2 adults and neither are registered would be 0.22 squared, which gives 0.048 as our answer. Let's take a look at a few more examples. Example 13. Andrew's 55 and the probability he'll be alive in 10 years is 0.72. Ellen is 35 and the probability that she'll be alive in 10 years is 0.92. You can see on the left, I've written these probabilities in symbolic form. And what we're trying to find is the probability that A, or Andrew's alive, and E is alive, Ellen is alive in 10 years. So that's going to be the probability that Andrew's alive, 0.72, and tells us to multiply, times the probability that Ellen is alive, 0.92. So you can go ahead, put that in your calculator to calculate your final answer. And we get 0.662. For example 14, a quality control procedure for testing cameras consists of drawing 2 cameras at random from each lot of 100 without replacing the first camera before drawing the second camera. If both are defective, the entire lot is rejected. Find the probability that both cameras are defective if the lot contains 10 defective cameras and the cameras are drawn at random. Some important things from reading this is that we are doing this problem without replacement. That means, unlike the last example, in this example, we have dependent probabilities we're working with. So we're trying to find the probability that the first is defective and the second is defective. I'm writing DEF for shorthand for defective. So the probability that the first is defective, well, we know that there are 10 defective in the lot of 100, so it would be 10 out of 100, and tells us to multiply. And the probability that the second is defective, well, if the first one taken out is defective, then we'll only have 9 defective left. And if one camera is already drawn, then instead of 100 cameras, we have 99 cameras left. So now what you can do is you can multiply across the numerator, multiply across the denominator, and then simplify your answer. We'll get the probability is going to be 1 out of 110, which is approximately 0.009. Our multiplication rule works for more than 2 events, as we can see here in example 15. Find the probability of a heads from a coin flip and a 5 from a dice roll and an ace from a deck of cards. The probability of a head from a coin flip is 1/2 and tells us to multiply. Probability of a 5 from a dice roll will be 1/6 and tells us to multiply. And probability of an ace from a deck of cards, well, that's 4 out of 52. Multiply across. Get 1 out of 156, which is approximately 0.006. Another popular type of problem we're going to encounter with conditional probability involves tables. Here we have a table with men and women divided into categories ranging from non-smoker to heavy smoker. Let's try some problems. If one of the 1,156 people is randomly selected, find the probability that the person is a man or a heavy smoker. You can see I've labeled the table with the different abbreviations that I'm going to use, and I've written out our formula. Probability of a man or a heavy smoker equals the probability of a man plus the probability of a heavy smoker minus the probability of that someone is a man and a heavy smoker. So the probability of someone being a man would be the total of 601 men out of the total of the whole table, 1,156. The probability of someone being a heavy smoker would be the total number of heavy smokers, 88, out of the total number of people in the table, 1,156. The probability of someone being a man and a heavy smoker would be, we'll find out where the men and the heavy smokers meet. So men goes across this way, and heavy smoker goes down. So the men who are heavy smokers, there's 49 out of 1,156. And you can see clearly that 49 men is both in the heavy smoker column, that total of 88, and in the total of 601 men. That's why we need to subtract it. So add and subtract across to get your final answer. We get a final answer of 640 over 1,156. That reduces to 160 over 289, or approximately 0.554. In the next example, we're asked, given that a woman is selected, what's the probability that the person's a heavy smoker? So probability of a heavy smoker, given that we have a woman, means we're only looking at the woman. So I'll only look at the row of women. That means our denominator is out of the total women. So looking at the women, there are 39 heavy smokers. So we have 39 over 555. Simplifies to 13 over 185, or approximately 0.070. For our last example, it says, given that a heavy smoker is selected, what's the probability that it's a woman? So you can see that we have a reverse from the last problem. Will our answer be the same? Let's find out. So we're only looking at the heavy smokers because it says given that we have a heavy smoker. So our denominator is 88. Our numerator will be the number of women out of that 88, which is 39. The reduced answer is 39 out of 88, or 0.443. Go ahead and try the rest of the problems in this packet and check your answers with the solution key. Let me know if you have any questions.